learn like a pro.
All right, let's dive in. Today, we are heading on a journey across one of the most amazing maps ever created, the periodic table of elements. We're going to explore this epic showdown, the one between the two biggest families out there, the metals and the non-metals. So let's get right to it.
Okay, so think about this for a second. What's really the difference between, say, a shiny metal pot in your kitchen and a simple piece of chalk? I mean, one you can bend, right? The other just shatters. One gets hot and cooks your dinner, the other, well, not so much. The secret behind all this isn't just what they are. It's about where they live on the periodic table. It's like their address tells you everything about them.
Now, before we really get going, we've got to know how to read our map. And that means understanding two key things, periods and groups. Honestly, once you get these, you've pretty much got the key to the whole thing. Okay, first up, periods. Super simple. These are just the horizontal rows you see going across the table. You can think of them like streets. And here's the cool part. Every element on the same street, or in the same period, has the exact same number of electron shells. For our trip today, we're going to be cruising right across period 3.
And then you've got the groups. These are the vertical columns, the ones going up and down. If periods are the streets, then groups are kind of like the families living on those streets. And elements in the same family, well, they act alike. They have similar chemical personalities. And that's all because of the electrons in their outermost shell. And trust me, those electrons, they're the real MVPs here.
So here it is, our grand tour for today. We're starting way over on the left with good old sodium, then heading right through magnesium and aluminum. We'll make a pit stop at silicon, and then cross over to the other side to meet phosphorus, sulfur, and chlorine, before finishing up with argon. I promise you, you're going to see a massive personality change as we move from left to right.
All right, let's kick things off on the left side of the table. This is metal territory. Our first stops are sodium and magnesium, and these guys are textbook metals. They're shiny, they conduct electricity, and most importantly, they've got a very particular way of doing things. They're givers. Now, to really get why they're givers, we absolutely have to talk about valence electrons. These are, without a doubt, the most important electrons an atom has. They're the ones on the very outside edge in the outermost shell, and they're responsible for literally all the action, how an element behaves, what it bonds with. It all comes down to these guys. And here's a little pro tip for you, a cheat code that's built right into the periodic table. Finding the number of valence electrons is so easy. Just look at the group number. For sodium in group 1, it's got 1. Magnesium in group 2, yep, it's got 2. And what about chlorine, way over in group 17? Well, for those groups from 13 to 18, you just subtract 10. So 17 minus 10 is 7. It's a super simple trick, but it tells you so much. So here's the bottom line. Metals, like sodium with its single lonely valence electron, don't hold on to it very tightly. It's kind of out there all by itself. So it's just way easier to let it go, to give it away. And when an atom loses a negative electron, what's left? A positive charge. So it becomes a positive ion. That's why we call them givers. Generous, right? Okay, let's keep moving. As we get closer to the middle of the period, things start to get a little weird. This is where we meet the elements that can't quite make up their minds. We call them the in-betweeners. This is the perfect example of their little identity crisis. Look at aluminum. When it forms an oxide, scientists call it amphoteric. It's just a fancy way of saying it can't decide who it is. Seriously, you put it in acid and it pretends to be a base. Then you put it in a base and suddenly it's acting like an acid. It plays for both teams. This is a huge clue that we're leaving metal land behind. And its next door neighbor, silicon, is pretty much the poster child for this whole in-between thing. It's a metalloid. So what does that mean? Well, it can look shiny like a metal, but it'll break just like a nonmetal. It kind of conducts electricity, not great like a metal, but not horribly like a nonmetal either. It's a semiconductor. It really does have a foot in both worlds. Okay, we've crossed the border now. We're officially on the right side of the table, and this is non-metal country. We're talking about phosphorus, sulfur, and chlorine. And you're going to see that their whole vibe is the complete opposite of the metals we started with. These guys, they are takers. You can see this personality shift perfectly just by looking at their oxides. See how it works? On the left, the metals like sodium and magnesium form basic oxides. Then, boom, you hit aluminum in the middle with its can't make up its mind amphoteric oxide.
And then you cross over to the nonmetals, and their oxides, silicon, phosphorus, sulfur, chlorine, they're all acidic. It's this beautiful, smooth transition all the way across. So why takers? It all comes back to those valence electrons again. Let's take chlorine, right? It's in group 17, so it has 7 valence electrons. 7! It is so close to having that perfect stable set of 8. There's no way it's going to give up 7 electrons. It's so much easier to just snatch one more to complete its shell. And when it grabs that extra negative electron, the whole atom becomes a negative ion. So you've got your givers, the metals, and you've got your takers, the nonmetals. So what do you think happens when these two meet? Well, this is basically the entire story of chemistry. It's all about finding stability. It's a classic chemical showdown. When a giver metal meets a taker nonmetal, like our friends sodium and chlorine, it's a done deal. The metal just gives its electron away, and the nonmetal takes it. That's an ionic bond. But what happens if 2 takers meet, like 2 chlorine atoms? Well, neither of them wants to give up an electron, so what do? They share, and that, my friends, is a covalent bond. You know, I absolutely love this analogy. It just makes perfect sense. Sodium is like a person who can't wait to give away their $1 extra. Chlorine is desperately looking for just one more. When they meet, the dollar is transferred instantly. It's so true, right? Sodium is just itching to get rid of that 1 extra electron, and chlorine is just one short of being perfectly happy. They're a match made in heaven. The electron jumps over, and bam, you've got sodium chloride, otherwise known as table salt. Okay, we've made it. We're at the very end of our road trip across period 3. Our final stop? Argon, over in group 18. But something's different about this guy. Argon is, well, it's kind of a loner. It's super unreactive. It doesn't want to give electrons, it doesn't want to take them. So what's its deal? And here it is, the big secret. Argon is a noble gas. Remember how everyone else was trying to get that perfect, stable outer shell of 8 electrons? Well, argon already has it. It was born with it. It's already achieved that perfect stability all by itself. So it has absolutely no reason to give or take electrons. It's just content. It's like the Zen master of the whole periodic table. So we've been going across the table this whole time, right? But what happens if you change direction and go down a group? Well, as you go down, the atoms actually get bigger. This means their outermost electrons are way farther from the center, from the nucleus. And just think about it. It's a lot easier to lose something that's far away from you than something you're holding close, right? And what do we call elements that are great at losing electrons? Metals. So the big takeaway is, as you go down a group, elements get more metallic. Okay, for our final face-off, let's put our 2 main characters head to head, sodium versus chlorine. In one corner, sodium, a silvery solid, a fantastic conductor, and its main move, losing 1 electron. In the other corner, chlorine, a greenish-yellow gas, a total insulator, and its signature move, gaining 1 electron. They couldn't be more different, and it's all because of their address on the table. All right, you ready? Time for a lightning round to see what's stuck. Let's go. What's a horizontal row called? A period. Do metals tend to lose or gain electrons? They lose them. What kind of oxide does a typical metal form? Basic. An element in group 17 has how many valence electrons? 7. What do you call an element with properties of both metals and nonmetals? A metalloid. Does aluminum oxide act as an acid, a base, or both? Both. What type of bond involves sharing electrons? Covalent. Why are group 18 elements so unreactive? Because they have a full valence shell. As you go down a group, do metallic properties increase or decrease? They increase. And last one, which element is in period 3, group 2? It's magnesium. Awesome job. So let's end with this one big idea. We've just seen that an element's entire personality, how it acts, who it bonds with, what it wants to be, is all determined by its address on this simple grid. So if something so fundamental can be so beautifully ordered, what does that tell you about the underlying rules of our entire universe? It's pretty mind-blowing when you think about it. Thanks for joining me on this journey,